In this video, we'll discuss strong acids and bases in buffer solutions. So what is a buffer? It's a chemical that when we put in a strong acid like HCl or a strong base like NaOH, it resists changes in pH. But how does it do this? Well, a buffer is nothing more than just a mixture of a weak acid and its base form. In equations, it's written like this, where the HA is our weak acid that is broken down to form a base. And to be more specific, since we start with an acid and formed a base after it's put in water, it would be called our conjugate base. So in problems, you might be told that you're starting with an acid buffer, and in that case, when we put it in water, you form some conjugate base. But the opposite can be true too. You might be told that you're starting with a base buffer, and in that case, the HA would be your conjugate acid. So it depends on what you're starting with. Buffers are always a weak acid or a base, which means that even though this arrow is going from left to right, in reality, it's actually a mixture in water. So if you put this weak acid or base in a beaker of water, you'll have a mixture of that weak acid and its conjugate base. So let's say the pH of this solution is 5, and we threw in a really strong acid like HCl. Notice that we have 3 A-minuses, our bases, in the solution. If we put in one equivalent of HCl, it will react with one of these 3 A-minuses, so that by the end of it, this A- becomes an HA. So you can kind of think that this HA A- mixture is essentially absorbing the HCl. And this will keep going until all the A- are used up. And now eventually there will be no more of these conjugate bases, right? That is the point in which we lost our buffering ability. As we add more of our strong acid after this point, it doesn't have any more A- base to react with and disassociates into H+ and just floats there. So now that our H+ concentration is increasing, our pH will now start to decrease. And the exact same thing can be said about a strong base like NaOH. It reacts with the acid form, A-, and if we have enough of these, we will completely deplete all of our acid, and any more of our strong base will allow NaOH to disassociate into OH-, which will increase our pH. So let's do a problem. 50 milliliters of 0.2 molar NaOH is added to 200 milliliters of 0.1 molar formic acid. Water is added to give a final volume of 1 liter. Determine the pH of the solution. So the pKa of formic acid is given at 3.75. So we know right off the bat the NaOH is our strong base, which means the formic acid is our weak acid, our buffer. First, we'll write out our equation. So since we're starting with formic acid, we would call the A- our conjugate base. NaOH is a strong base, so that will react with our acid buffer. So we'll put the NaOH on the left side, and we know it disassociates to form OH-. Next, we'll set up our ice table. Remember, everything here is in the units of moles. So the molars and volumes from this problem can be multiplied to get us these moles. 0.2 molar is the same thing as 0.2 moles per liter. And since we have 50 milliliters, we're going to have to convert that to liters. Once we do that, we can just cancel out the signs, which gives us 0.01 moles of OH-. So we'll put in 0.01 for our OH- and have our next molar and volume pairing. We'll give it the same setup. And as we cross out like units, we get 0.02 moles of our HA. We'll put that into our table as well. And remember, all of this OH- will react with the HA until one of these guys run out. In this case, the lesser one is OH-, so both of them on the same side of the equation decrease by 0.01. And for the C row, whatever we subtract on one side of the equation, we add on the other. And so by the end, we have 0.01 each of our HA and A-. Since we have a final volume of 1 liter, we divide both moles by it to get us our molars. And then using this pKa, we will plug everything into the HH equation to get us our pH. Once we do that, we get us a pH of 3.75. Let's do another problem. A buffer with 0.35 molar base and 0.4 molar conjugate acid has a pH of 8.5. Determine the pH after 0.004 moles of HCl is added to 0.1 liters of solution. First, we identify our weak acid and base. We write out its dissociation equation, and we have HCl, which is a strong acid. We know acids interact with bases, so we'll add that HCl on the right side of the equation. So we'll fill in our ice table from here, which, as a reminder, is in the units of moles. The molarity and volume multiplied together gets us moles, so we'll use that to set up our equation like this, in which our liters cancel out to get us the moles. The same thing can be done for the conjugate acid, which gets us 0.04 moles. The HCl is already in the units of moles, so we can just plug that in as is. The side with the strong acid is the one that will reduce by the smaller value, so in this case by the 0.004 moles. And what we decrease on one side, we add on the other. So in total, we get these values. We'll plug those values into our HH equation, but we have a problem. We don't know the pH or pKa at this point. But what we do know is that at 3.5 and 0.4 molars, our pH is 8.5. So let's pause where we're at with this so we can find the pKa at that point. So we'll put in the pH of 8.5 for when the base buffer back then was at 0.35 and our acid was that of 0.4. Now we can find the pKa, which gets us 8.56. Again, we'll use this for the equation we were trying to solve beforehand. And now when we put this in our calculator, our pH is 8.41. So let's do another problem. A solution of weak acid is completely protonated at a pKa of 3. Determine the equivalence of base needed to reach a pH of 2. First, we'll write out our HH equation, where we know our pH and pKa values. For the time being, our A minus over HA can be treated as one thing that we'll call X. And from here, we'll solve for X, which gets us 0.1. And remember, this variable is our A minus over HA. Another way to write 0.1 is like this. So essentially, our A minus is 0.1 and HA is 1. Next, we'll write out our dissociation equation. And notice we need to introduce a base. And since bases interact with acids, we know that will go on the left side of our equation. From here, we'll write out our ice table. We know that we're completely protonated. That's just another way to say that we're completely in the HA form starting out for our buffer. So we can arbitrarily put in 1 for HA and 0 for A minus. So essentially we have two equations. First, HA and A minus added together makes up 1. And we know that A minus over HA is 0.1. So we can solve for one of these variables and plug it in for the other. It doesn't matter which one, so let's solve for A minus for the right equation. We'll move the HA over. Next, we'll plug this A minus value in for the left equation, divide both sides by 1.1, and we get 0.91 for our HA. So we'll replace the HA with this value and solve for our A minus. So essentially, this is our ending point once we get to a pH of 2. This means that these two values act as the ending point, the E for the ice table. To go from 0 to 0.09, we must have added 0.09 of our A minus. And what we add to one side of the arrow, we subtract the other, which means we must have started with 0.09 of our base. And so that's our answer. We need 0.09 equivalents of base to reach a pH of 2. in making 1 liter of 0.1 molar buffer solution at pH of 8, determine what would be mixed given the following are available. 0.2 molar acid buffer, pKa of 6.76, 0.5 molar HCl, 0.5 molar NaOH, and unlimited water. So we know that we have pH and pKa values here, which we can plug into our HH equation. So we want to get to a pH of 8, but we don't know what our A- and HA are. For now, we can set that whole fraction as x, and from there solve for it. So we move the 6.76 over, cancel out log, and get 17.38 for our x, which remember is our A- over HA. So we know the proportions of A- and HA, but there's a second equation we need. How many of the buffer do we have in total? For that, we know our ending molars and volume of our buffer, so we can use both to find the total moles. 0.1 molar is basically 0.1 moles per liter, and that liter will be on the top so that it cancels out the liters, which once we do that, we get 0.1 moles. So now we have the two equations to solve for A- and HA. We can solve for the variable for either of the equations. It doesn't really matter which one. Let's just do the one on the right. We'll move the HA on the right side, and we'll plug that in as our A- for our left equation. Once we do that, we divide both sides by 18.38, and we get an HA value of 0.005 moles. To find A-, we can just plug this value into this equation, and once we do that, we get a value of 0.095 moles. So basically, these are the proportions that we need to end with the E in the ice table. So what do we start with? Notice we're specifically using an acid buffer, so that just means starting out, the I in the ice table, we're completely in the HA form. So we'll put that into the ice table. First, write out our dissociation equation. Then we know that we're starting with 100% of the acid form of the buffer, the HA, and we know what our ending values are. To get to these final values, we know the change, the C, is like so. The side that is decreasing, our HA, is decreasing because it's being reacted with something. Since HA is an acid, that means it's being reacted with a base, which means this also drops by the same amount. And one of these guys on the same side of the arrow will always go down to 0. Since HA doesn't go down to 0, that means it will be our base that goes to 0. And to drop this 0, this means that we must have started with 0.095 moles of base. So we'll be using the strong base NaOH rather than the HCl, which is a strong acid. Now that we have our moles of NaOH, our question becomes, how do we get from 0.5 molars to 0.0095 moles? As we know, molars is just moles over liters, so we have to multiply it by a certain volume to get to said moles. For that, we'll use the MV equals MV equation, where each side is just the moles that we have. So on the right side, we can just put in the moles that we want to get to, and on the left side, we'll plug in the molars and solve for V, which gets us a volume of 0.19 liters. Now, let's solve for the buffer. First, we know we're starting with 0.2 molars of it, and we already have the molars and volume of what we need to end with. And so, solving for V, we get 0.5 liters of the buffer. These two volumes added together accounts for 0.69 liters of the solution, but we want our final to be 1 liter. So that means the remaining will be our water, which happens to be 0.31 liters of it. So altogether, to make this buffer solution at a pH of 8, we'll need 0.19 liters of NaOH, 0.5 liters of buffer, and 0.31 liters of H2O.